So what I'm going to tell you a little about is the spin polarized transport. That is commonly used in many of the magnetic materials. We are going to see this field is known as spintronics. So let's start from the very fundamental, so the concept of the atom. You are quite familiar with how small the atom is. The size between the difference between Earth and a ping pong ball is roughly the same between the ping pong ball and the atom. Now you can appreciate how small an atom is. And the atom is usually the fundamental building blocks for many, many materials, like a molecule in water and air, and organic molecules, as well as the gene and life. They can also be used for many artificial constructions of nano devices, and also big constructions such as satellite or any of the buildings. I make some room here. Okay, what we are interested in today is the electrons. If you take a look at the atom, it has a solid core in the middle. It's a nucleus. The size of the atom is typically on the order of 10 to the minus 10. And the size of the nucleus is on the order of 10 to the minus 15. You see that there's a huge amount of space that was actually filled up by electrons. The size of the electron is extremely small. It is beyond any detection limit. So for any practical purpose, we will consider it as a point charge. Okay. So an electron is a charged particle, and it also carries a very important property is known as the electron spin. The spin is, let's consider any object that's spinning around a certain axis. It has a certain angular momentum. And because of quantum mechanics, such angular momentum is actually quantized. The reason we do not feel it in our daily life is because this quantum is extremely small. It is on the order of 10 to the minus 34. And whatever we are dealing in the normal life is roughly on the order of 1. So we barely can feel this particular thing until you get to extremely small things, such as the electron. A typical electron carries the angular momentum. We call it a spin. That is a spin 1/2 particle. And that corresponds to an angular momentum of 1/2 of h bar. So for this particular system, the spin is an intrinsic property. You should not think of an electron is spinning around a certain axis. It's actually intrinsic. It's not an object that's moving in that way. So it's a totally different concept, although it shows up as an angular momentum. So suppose in the macroscopic world, if we have a charge moving around the axis, it will produce a magnetic field. This magnetic field will be opposite to the direction of the angular momentum if the charge of the particle is negative. So we can see that motion of the angular momentum of a charged particle can produce a magnetic moment. The same thing happens for an electron. If we assume the electron is rotating around the axis, the spin of the electron will produce a magnetic field. Let's say we should say a magnetic moment. And the magnetic moment is actually the origin of many of the magnetic phenomena you see in the nature. But again, I have to correct that you should not think an electron is spinning around a certain axis, because there is essentially no volume of electron. If we really assume such a picture and assume the charge is rotating around the axis, you can calculate the size of the electron, which will be comparable to a proton. That is totally wrong. So this picture is not right. I just put it up so you can understand it much easier. Okay. So there's a very important consequence because I mentioned it is a spin 1/2 particle. Therefore, it is a fermion. For any particle with an integer spin, we call it a boson. A boson particle follows the Bose-Einstein distribution. You can take a look at this is the distribution formula dependent on the energy and the temperature. If we look at a very high energy, you can see this term is exponentially large. The whole thing is actually decaying exponentially, so it's vanishing very fast. Now if we look at a small energy, if you do a Taylor expansion, you would find that the distribution would be inversely proportional to the energy. Therefore, it is diverging near zero. There's a very interesting phenomenon. Assume we have a zero temperature, and in that case, if you have any finite energy, this term will be infinite. As a result, there will be no any states at zero temperature. Everything will be condensed at zero, the ground state. This is commonly known as the Bose-Einstein condensation, a very interesting phenomenon for bosons. The electron is a fermion. It follows the Fermi-Dirac distribution. Here is the formula. And there is a very important constant. We call it the Fermi energy. Now let's look at this term. If the energy is higher than the Fermi energy, this term is positive. And this term will be vanishing exponentially as a function of energy. Therefore, the distribution will go to zero extremely fast beyond this Fermi energy. Now, if the energy is less than the Fermi energy, this term is negative, and it will vanishing very fast to zero. So the whole thing will become 1. So this plot illustrates how the distribution will look like. It will have a finite distribution of 1 until it reaches the Fermi energy. The distribution, the probability will drop quickly to 0. So this kind of construction gives us a very interesting phenomenon, the Fermi surface. Now you can imagine we have a system. I draw it in the K space. K is basically corresponding to energy. Now if you put electrons in there, it will start going from the center, going up and up and up. So what you are doing, you are just filling a ball. So, and this ball has a surface corresponding to the Fermi energy, and this surface is called the Fermi surface. In the free electron model, this surface is just a sphere, but in reality, it's usually totally different. And the Fermi energy, if we use a free electron estimation, it is only dependent on how many electrons you have per unit area. So it's dependent on the density of the electrons. Okay. Now let's summarize the important facts of the electron. The first, most important part, it is charged. It carries a finite charge. That allows us to move the electrons around by electric field or magnetic field. The next important property is that it is extremely small. It can fit in any space, and it has a small mass. The mass of an electron is 1800 times smaller than a proton or a neutron. For that reason, if you apply either electric field or a magnetic field, the particle will be accelerated very fast. So it's a highly mobile particle. Because of these three particular properties, an electron can be used to construct a very fast electronic device. This is the modern technology, the electronics. We will take a look at the other two important properties. The angular momentum. An electron carries the angular momentum of 1/2. One important feature after that is the Fermi distribution and the existence of the Fermi energy. And the other very important consequence is that because of the spin, there is a magnetization associated with every electron. And this is the fundamental, this is behind almost any of the magnetic phenomena we are looking at in the nature. Okay, so let's go to the main topic, spintronics. You know, the word spintronics is basically adding spin together with the electronics. In a traditional electronic device, we use the transport and storage of electron charge for the information technology. In spintronics, we have another degree of freedom. We have the electron spins. And by using that, we can construct novel devices with unprecedented functionalities. Basically, you can get a better performance and many new functionalities. The spintronics is actually quite close to you already. The very good example is the discovery of the giant magnetoresistance and the tunnel magnetoresistance effects. They are quite widely commercialized already. And there are many other research topics in spintronics. I'll try to pick a few topics just to quickly illustrate to you. A transistor. A spin-based transistor takes advantage of the field effect. What is really behind it is the special relativity. Now you can imagine if we have an electron flying through this channel, the electron has a finite velocity, and we can apply an electric field, we call it a gate voltage, to modulate the electron spin orientation. What happens is, if you look at in the rest frame of this electron, the electric field will actually transform into a magnetic field. Then the electron will start processing around this magnetic field. That's how you can change the orientation of the electron by electric field. Basically, you are changing the magnetization by electric field. This is called a data death type spin transistor. And by that kind of manipulation, you can achieve a transistor-like performance. The next thing we are interested in is in the spin-based optoelectronic devices. It is quite widely known that if you use a spin-polarized charge carriers, the light-emitting diode efficiency as well as the solar cell efficiency will be significantly enhanced. We are more interested in a different fact that a spin-polarized charge carrier can be readily converted into a circularly polarized light. This light can travel extremely far, and the light can be collected and using exactly the reverse process and can be converted back into a spin information. Therefore, in spintronics, it is possible to transfer the spin information over extremely long distance by optical method. Next, you heard about quantum computing. An electron spin is probably the simplest system out there. It is a quantum two-level system and is very suitable as a qubit. For a qubit operation, you need some way to write the spin information and to detect the spin information. And also, you need some way to manipulate it. The spintronics can actually come in to perform these tasks. Our development in spintronics will eventually allow us to build quantum computers in a solid-state system. You don't need ultra-high magnetic field or ultra-low temperatures. Let me introduce to you the concept of magnetoresistance. This is probably one of the most development in spin-polarized transport. Magnetoresistance is the resistance change of the system when its spin configuration is modified. For example, we will use a GMR. It stands for giant magnetoresistance as an example. Just a reminder, GMR and TMR stands for giant and tunnel magnetoresistance. Now, in a traditional GMR device, it has a multi-layer stack, alternating magnetic and non-magnetic films in this configuration. Now, if we send a current through such a device, the electron will suffer a lot of spin-dependent scattering. That will increase the system resistance, and the system goes into a high resistance state. Now, imagine if we apply a large magnetic field. All the magnetic layers will be aligned parallel to each other, and the system will go to a low resistance state. Therefore, we can change the resistance of such a system by changing the magnetic configuration. This kind of geometry is called current in-plane configuration because the current is flowing inside the film. The reason I use the GMR as an example is this is essentially the legendary story of spintronics, and it was an awarded Nobel Prize in 2007. In the modern technology, it has evolved so much that the size of the device is much smaller than the film thickness. They now look more like a nanopillar, like this, and has many, many more complicated structures. This kind of configuration is called current perpendicular to plane configuration. One important thing I'd like to point out here is a magnetoresistance device can be configured into a magnetic sensor or into a magnetic memory configuration. In the former configuration, you can see the resistance of the system varies almost linearly as a function of the magnetic field. So this is a very sensitive magnetic sensor, although not as good as a squid. The sensitivity of a squid is roughly 10 to the minus 15, although that's a sensitivity. for the GMR and TMR heads, they are roughly 10 to the minus 10. So approximately 5 orders of magnitude worse than the squid. But the advantage is these guys can perform at room temperature and far beyond. In the second configuration, we call it a memory configuration. As you can see, there are two very stable resistance states corresponding to low and high resistance and the digital 0 and 1 states. Therefore, such a device can be used very nicely in memory configuration, such as we call it a magnetic random access memory. The figure of merit for magnetoresistance is defined as a ratio. The ratio of between the change of the resistance relative to the normal resistance. So why are we interested in magnetoresistance? I put a few examples for its application. The importance actually is because magnetoresistance can directly convert spin information into electronic information. So it's directly linking these two worlds, the spin and the electronic world. The first best example is probably a hard drive. In every hard drive, you have a very sensitive read head. That is made out of these such magnetoresistance devices, and it can be used to read out the information encoded on the flying disk. Because of the sensitivity of these magnetoresistance devices, they can be used to map out a magnetic field distribution outside, for example, a silicon chip. You can use this information to reconstruct what the current flowing is inside the chip. This is a non-destructive way to look at what's happening inside the IC chip. And one of the most and the latest development in magnetoresistance device is the magnetic random access memory. In such a memory device, the data you put in the memory is non-volatile. They will stay there essentially forever without any power because they are stored in magnetic units. And the device is very dense. It has a high density and has a very high speed. Essentially, it has a better performance than any other memory technology. It has the advantage of, for example, it can integrate the DRAM, the hard drive, and whatever flash into the same unit. This type of memory is usually referred as a universal memory. Of course, it has a disadvantage. Its cost is much higher, like 10 times higher than flash. That's why you are using flash instead of these guys nowadays. But it also has a big advantage. It can essentially be used in any environment. So, for example, the military people are especially happy with the development of MRAM because the performance of MRAM is simply unrivaled compared to any other memory technology. You can use it in, for example, in deep space. You could not use a flash drive up there. The next breakthrough in terms of magnetoresistance is the discovery of so-called spin transfer torque. I will just give you an example. It turns out if you send a DC current through a magnetoresistance device, you can drive the nanomagnet into persistent precession. It will start precessing around the axis, and the frequency of such a precession is roughly on the order of gigahertz. Therefore, such a device can be used as a microwave generator, and you can put it in your device wherever you want. It is an on-chip microwave generator. Another advantage of such a device is that the frequency of this device is readily tunable by the current density. You can change the frequency wherever you want. Now let's start from the very beginning to tell you the concept between ferromagnetism and the superconductivity in the next slide. In the ferromagnetic material, the simplest picture is that all the electrons are actually aligned parallel to each other because of the existence of exchange energy. The exchange energy will try to align everybody parallel, and the typical energy scale is on the order of 1 electron volt. This is the reason why a magnetic material is magnetized, because everything is aligned. Let me try to explain a little bit about this exchange energy. It actually comes from the Pauli exclusion principle, which basically means two electrons cannot occupy the same states if they have the same spin. That said, if the two electrons have opposite spins, their spatial wave function will be symmetric. Its distribution will look more like that. Well, if the two electrons are aligned parallel to each other, this is the triplet state, the spatial distribution will have to be antiparallel, antisymmetric. So it will have a node in the middle. Because of the different spatial distribution of the wave function, that leads to a very big difference in there. If you put the Hamiltonian in there, I won't go into the details, you are going to see a big difference between these two states. So the simplest version I'll put here, suppose we have a wave function of x plus minus y because of the two different configurations. If you look at the expected value of the Hamiltonian, what you get is a fixed term, and another term. That will depend on the sign. This is a very simplified version, and it's actually not right. But what you see is there will be a term, depends on the polarity of that wave function. And this term is the basis of this exchange energy. The reason we call it exchange is the cross term between these two. It's not like just a square. Okay. The next phenomena is the superconductivity. This is a totally different phenomena. Imagine this is the electron Fermi sea. As I mentioned earlier, the electrons will start piling up until they form a ball. The two electrons on the surface of such a Fermi sea will try to pair up to form a Cooper pair. The typical pairing energy 10 to the milli electron volts. So the theory behind that is known as the BCS theory, Barney, Cooper, Schrieffer, in the year 1957. They were awarded a Nobel Prize 1972. I'll put up a very simplified version of this BCS theory also. The interaction energy between two electrons, this term, is depending on this term. We'll ignore. It's not important. There's nothing we are interested in. And another term. This is the important term. Here, omega means the energy difference between these two electrons. And omega Q is the phonon energy. Now you can see one interesting phenomenon. No matter how weak this phonon interaction is, there you can always find close enough energy between the two electrons, and this whole term will become negative. That means the two electrons can have an attractive force, no matter how weak your phonon interaction is. This is the fundamental knowledge behind the BCS theory. The two electrons will have an attractive interaction, and they pair up to form the Cooper pairs. Okay, now we move on to the next part. We call it a superconducting spin valve structure. This is some of the work I did before at MIT. As I already mentioned, a magnetic material align all the spins parallel to each other. Now in a superconductor, they antiparallel to form Cooper pairs. Naturally, if you put a ferromagnetic material on top of a superconductor, the superconductivity will be strongly suppressed. Imagine we have a sandwich structure with two magnets and a superconductor in the middle. If we align them parallel to each other, the superconductivity will be destroyed. If we align these two ferromagnetic materials antiparallel to each other, their effect will be cancelled out and the superconductivity will be restored. So we can expect a very large resistance change because we can turn the superconductivity on and off by spin manipulation. There are a few different ways to achieve such a goal. I will skip the details and let you see some of the experimental results. Firstly, this is a system based on BCC iron, vanadium iron superlattice. Epitaxial stands for basically means the system is a single crystal, and BCC means the body-centered cubic. It's the structure of the system. And vanadium is the superconductor material we use here. Its transition temperature is roughly 5.4 Kelvin. The whole stack was deposited onto silicon wafer with an MgO buffer layer in an MBE system. Now let's take a look at the first piece of information. We plot the transition temperature as a function of thickness. As you can see, the transition temperature is clearly inversely proportional to the thickness. This is quite well known in the literature because the transition on the surface of every superconductor, there is an inactive surface layer. The reason of that is the electrons on the very surface do not have enough neighbors. So on the other side is a vacuum. So they do not have a neighbor to pair up to form Cooper pairs. So the surface layer will usually do not have superconductivity. Now it follows the simple equation. The Tc is inversely proportional to the thickness, and the inactive layer thickness B we can deduce from the slope, and it turns out to be 0.18 nanometer. This is only just one atomic layer. That means the vanadium film we fabricated this way, it has extremely high quality. The other parameters, this is the electron density and the coupling energy. So these are constants. Okay. The second piece of information showed you the critical field. We call it upper critical field because the vanadium is a type 2 superconductor. It will have two critical fields. So this upper critical field square clearly depends linearly on the temperature. This is already known in literature because this is a two-dimensional behavior, and our vanadium film is a film. It is a film, so it behaves in the two-dimensional. So the critical field should follow this equation. The square of the critical field will be linear in T, and then from the slope we can calculate this guy, and this guy it has a term tells us the coherence length in this film. It's about 13 nanometer. A bulk vanadium is approximately 44 nanometer. The reason the coherence length is smaller in the thin film because the mean free path, the electron scattering length, is limited by the film thickness. The third piece of information is a little bit hard to understand. You see that the transition temperature of the system is a non-monotonic oscillating function as a function of the ferromagnetic layer thickness, the ion layer thickness. The reason is that when the Cooper pairs enter the ferromagnetic material, they will feel this very strong exchange interaction. And one of the electrons will be actually accelerated, the other one will be slowed down. As a result, the whole Cooper pair will gain a center of mass momentum. Then the wave function will start oscillating as a function of thickness. When the Cooper pair reaches the other boundary, they will be reflected back. And because of the oscillation in phase, they can be either destructive or constructive. This oscillating behavior is actually the interference between the propagating wave and the reflected wave. Okay, now let's take a look at this magnetoresistance measurement. What you are looking at is a plot of the resistance as a function of field as well as the temperature. Let's cut one slice out of it and put it here. You see there are two very well-defined resistance states. It means we have a large magnetoresistance here. This is the field. These two states corresponding to the parallel and antiparallel configuration between the two ferromagnetic layers. The zero resistance state clearly is a superconducting state, and the finite resistance, the normal state. We see that we can turn the superconductivity on and off by manipulating the spin information. If we use the traditional definition of magnetoresistance, the change of resistance divided by the resistance, we get an infinite. So that means that basically because anything divided by zero is infinite. I want to point out here that the spin-dependent scattering, like in giant magnetoresistance effect, is not responsible for what we are seeing here. What we are seeing is only the manipulation of superconductivity by spin configurations. Okay, we can take the system one step further to look at how to manipulate superconductivity locally. So we take advantage of the phenomena called magnetic domain wall. Now imagine we have a magnetic object and all the spins are aligned parallel to each other. This is actually energetically very unfavorable because you get a lot of magnetic poles on the surface. So the system will try to accommodate that by breaking up into domains, like in this configuration. Therefore, we lower the magnetic static energy significantly. But it comes with a catch. Let's take a look at the boundary between two magnetic domains. If the electron, if we have an abrupt change between the two domains, the two spins at the boundary will have opposite alignment. So that has a significant cost in terms of the exchange energy, because the exchange energy will want to align everything parallel to each other. So what the system does is it will try to spread the change over a very long distance. Now if you look at any two electrons neighboring to each other, the change between them will be extremely small. So the magnetic exchange energy will be significantly reduced. But this process cannot continue indefinitely, because there is another energy scale that will come in. This is known as the magnetic anisotropy energy. What this says is that because of the crystal structure, the electron spins will always try to align parallel to a certain direction. For example, if they like this direction and that direction, they will hate this kind of alignment. So the competition between exchange energy and anisotropy energy will define a finite width of this crossing. This is called a magnetic domain wall, and the typical size is on the order of 100 nanometer. A magnetic domain wall is a very, very stable magnetic object, and you can move it around by electrical current or by magnetic field. So with that in mind, we can construct memory device out of these magnetic domain walls. For example, if you have a nanowire with a lot of magnetic domain walls on it, you can drive these domain walls by applying a large electrical current. They will move by these detectors one by one, and you can read out the information one by one. So this is commonly referred as a racetrack memory developed by IBM. Imagine you have a million of such devices. You can store a whole bunch of data in these, because we are using a three-dimensional recording, unlike a hard drive. A hard drive is still a two-dimensional recording device. So the data density would be at least 100 times higher than a hard drive. Now this is what we use. We take advantage of the magnetic domain wall and to construct the superconducting spin valve structure. What you are looking at is a micron-sized nanowire. We have a certain patent nano constraints in the middle. The depth of these constraints are 200 nanometers. So the cartoon on the top illustrates how the system works. What we have is we have two very large pads on the two ends. These are the magnetic domain wall reservoir. They will nucleate magnetic domain walls and inject the domain walls into the wire. When the two domain walls move to the center, they will be strongly trapped at these nano constraints. And when that happens, these magnetic domain walls will generate a local magnetic field that will suppress superconductivity. Here, the inset shows you a mapping of the field distribution around this domain wall region. So when that happens, we are going to see a high resistance state in the wire. And if we apply large enough energy to drive the domain walls out of the system will return to its low resistance state. As you can see, not only we can control the superconductivity very nicely, we can also do it precisely and locally whenever we need and wherever we need. This slide shows you the actual result. As you can clearly identify, there are two very well-defined low and high resistance states. This is as a function of temperature. This is magnetoresistance versus field for different temperature. These two resistance states correspond to when the domain wall is in the middle of the wire or when they are driven out of the system. One very important and interesting phenomenon is the two magnetic domain walls can actually interact with each other. In the first configuration, we have two transverse domain walls. Transverse means their direction is perpendicular to the film, to the wire. We have these two transverse domain walls in the same polarity. If you look at the spin configuration, we are going from left, up, right, then back up, back left. So these two domain walls are actually just two separate 180-degree domain walls. And such a system can be easily annihilated by a reasonably small field. In the second configuration, what you are seeing is these two magnetic domain walls have opposite polarity. As a result, if you look at the spin configuration, it goes from left, down, right, then up, then left. The spins complete a whole rotation across the wire. So such a configuration is normally referred as a 360-degree domain wall, because the spins will have to complete a full rotation. And in such a configuration, the magnetic flux in such a device is closed. Therefore, such a domain wall configuration is extremely stable. And it is much harder to drive it out of the system. You see, we need 3 times higher magnetic field to annihilate such a structure. So the 360 magnetic domain wall is very stable, and for that reason, they can be used as a stable memory unit. Okay, now let's move on to the next part. I will introduce you to another magnetoresistance phenomena, the tunnel magnetoresistance. You've heard about the giant magnetoresistance, which is actually a semi-classical phenomenon. You can easily understand it by considering spin-dependent scatterings. But in the tunnel magnetoresistance phenomena, this is totally a quantum phenomenon, and there's no classical counterpart. What happens is that an electron can instantaneously disappear from one side of the tunnel barrier and appear on the other side. So, and the electron energy can be much, much lower than the tunnel barrier height, and they can still manage to get through. Therefore, it does not exist in any classical world. A typical magnetic tunnel junction will have 2 magnetic electrodes with an insulating tunnel barrier in the middle. If the 2 magnetic electrodes are aligned parallel to each other, the electron can cross the system very easily, and the system is in a low resistance state. Now, if we align the 2 magnetic electrodes opposite to each other, the electron will have a hard time to cross, and the system goes to a high resistance state. This is called the tunnel magnetoresistance. The history of tunnel magnetoresistance, it was discovered more than 30 years ago by Julia. But that time, the TMR is extremely low, and it's limited to very low temperatures. Then the development happened in the year 1995. Mudera and Miyazaki independently discovered that by using amorphous aluminum oxide tunnel barrier, the TMR can start operating at room temperature. In the year 2004, Parkin and Yuasa independently discovered that by using epitaxial MgO barrier, the TMR can reach well above 200% at room temperature. Now keep in mind, the TMR ratio, we would like it to be the higher the better, because we can get more signal out of the same system. This is how the system works. We started with the oxidized germanium barrier. The system is extremely weak, and the result is actually not reproducible. Then we started looking at amorphous aluminum oxide tunnel barrier. This is a very robust system, and the TMR starts to work at room temperature. The incorporation of epitaxial MgO tunnel barrier instantaneously brings the TMR value higher by a factor of 10, and it's reaching well above 600% by now. I'll put one slide to illustrate how we fabricate this so-called magnetic tunnel junction. We grow a whole stack of wafer with either magnetic layer, non-magnetic layer, and the tunnel barrier in the middle. And there are many layers below and many layers above. This is the main part. We can pattern the structure by either photolithography or E-beam lithography. Then we can do the hard physical ion milling. So this is a dry etching method. Basically, we use accelerated argon to knock out everything. Then we stop at the middle of the tunnel barrier. We can passivate the whole device with any insulator like silicon oxide. Then we either do a single-step lift-off process because we have a resistor here. If you do a lift-off, they are going to open up the tunnel junction area. We can either do that way, or we can do a very high-angle ion milling that will remove anything above a certain surface. That will expose the tunnel junction area. Then we can put on the top contact. This way we'll get the whole tunnel junction structure. It's a vertical three-dimensional structure. Okay, here is the history value, recorded value of the tunnel magnetoresistance ratio. Starting from the year 1995, it grows very steadily until the year 2004, the discovery of the MGO tunnel barrier. It really starts to shoot up. And at this moment, it has reached about 600% at room temperature. That enhances the recording density significantly. You probably already noticed your hard drive density is increasing exponentially. So there are quite a few different approaches to enhance TMR, so we can get a higher and higher signal and make the device much smaller. The first and the most natural way is we can enhance the spin polarization of the two electrodes. So what I'm illustrating here is the two bands of the spin up and spin down channels. So in the non-magnetic metal, the spin up and spin down electrons are totally balanced, and there is no any spin polarization in such a device, metal. In the ferromagnetic material, because of the exchange interaction, what the exchange interaction does is it will shift one band relative to the other one. Now if we take a look at the density of electrons at the Fermi level, we see these two channels are imbalanced. We have more up electrons than down electrons. The system is now called ferromagnetic. It has a finite spin polarization. In the very extreme case, the spin down band is completely shifted away from the Fermi level. And if you look at the electrons, it is completely dominated by spin up electrons. And the spin polarization at the Fermi level is 100%. This kind of material is known as a half metal. It's metallic in the spin up band, but insulating in the spin down band. There is a very simple formula called Julia's model, predicting what your TMR value is depending on the spin polarization of the two electrodes. As you can see, if the spin polarization of the electrodes goes to 100%, the TMR will diverge. It goes to infinite. That is the reason why people are trying to use materials with higher and higher spin polarization. Experimentally, the highest TMR realized using cobalt iron boron and amorphous aluminum oxide as a tunnel barrier is about 70% at room temperature. And at low temperature, if you use the LSMO as the metallic electrode and the STO as a tunnel barrier, the TMR is over 1,000%. Here, cobalt iron boron stands for it's an alloy with 20% of boron. With the boron incorporation, this metal becomes amorphous, and its spin polarization is roughly 50%. 50% will give you roughly 70%. Now, this LSMO stands for strontium-doped lanthanum magnetite. This is a half metal, and its spin polarization is almost 100%. That is why the TMR value is so large. It's not infinite, but it's extremely large. But this system, the performance of such a system is limited to low temperature only. Because normally half metallicity will decrease very fast with the enhancing of temperature. They do not work at room temperature. The next approach, as I mentioned, is by using epitaxial MGO as a tunnel barrier. In this situation, not only we conserve the electron spin orientation in the tunneling, we also conserve their Bloch wave function. A Bloch wave is the electron wave stays in any periodic solid state system. It's their angular momentum state, let's say that way. So here I illustrate how the band works for a body-centered cubic transition metal, like iron, for example. It can be decomposed into dirt 1, dirt 2, and dirt 5 states. These states will tunnel through the MGO tunnel barrier at a totally different rate. Let me put in a simplified version. What I am showing here is the Bloch state, the projection of the Bloch state onto the tunnel barrier. So you can clearly see for the electrons with the dirt 1 symmetry, they are highly symmetric and they match very well with the MGO tunnel barrier. And as a result, these kind of electrons decay very slowly inside the tunnel barrier. For any other states, they have lower symmetry and have a much worse matching with the tunnel barrier. Their decay rate are much faster. Here is the decay rate of the electron with different states as a function of the barrier thickness. This is the barrier region. You can clearly see the third one electron will decay the slowest. The next slowest decay rate for 35 electron. Because we are plotting the plot in a log scale, the small difference you see here is already 10 orders of magnitude. So therefore, for the tunneling of a BCC transition metal matching with the MgO tunnel barrier, the tunnel current is completely dominated by the dirt 1 electron. Fortunately for us, for BCC ion and cobalt ion, these are the systems we are interested in. The dirt 1 electrons are completely aligned in the up direction. So if you couple an ion with the MgO barrier, you are essentially building a half metal. They have almost 100% polarization. That is why the TMR is so large when you use the MgO tunnel barrier. At room temperature, it is already over 600% using cobalt ion boron coupled with the MgO. I think that corresponds to a spin polarization of roughly 80%. And at a low temperature, the TMR has reached way beyond 3,000%. Okay, what I'm going to introduce to you today is a totally new and novel phenomenon. We call it spin filtering. This is basically we are putting new functions into the tunnel barrier. And I illustrate a tunnel barrier here. Because of quantum mechanics, electron tunnel probability is exponentially dependent on the tunnel barrier height. Now imagine we use a magnetic material as a tunnel barrier. The spin up electron will see a low tunnel barrier height, and the spin down electron will see a much taller one. Therefore, the spin up electrons can cross the barrier very easily and will totally dominate the tunneling process. If we look from this side of the current, the tunnel current will be completely dominated by spin up electrons. Therefore, we call it a spin filter. It is extremely efficient because of the nature of quantum tunneling. And the spin polarization of a tunnel electron was demonstrated to be higher than 98%. The spin filter is not some mysterious material. They are actually a common property of any magnetic insulator. You see a lot of application with the magnetic insulators in your daily life already, like permanent magnet. Those black-looking rock-like permanent magnet, for example, you use on the blackboard, are most likely made out of those magnetic ferrites. And because these materials are magnetic, they have a very high permeability, and they are insulating. They are commonly used as a core material of electromagnet and transformer and inductor. Because they are insulating, when they are used in an AC operation, they will significantly reduce the eddy current loss. The eddy current loss is if you have alternating magnetic or electric field, you generate a current on the surface of any metal. But in an insulator, it's no longer such a case. So that's very important for a transformer. Also, because of their high permeability, they can be used as a RF filter or RF waveguides. Other thing of interest is the metamaterials. You probably have heard about this word. For example, you might see something like a super lens or invisibility cloak. Those are made possible because of the development of photonic crystals. In completely parallel to this system, we also have phononic crystals and magnonic crystals. Photon is an excitation of electromagnetic wave. Phonon means the vibration of the crystal lattice. And the magnon is suppose you have a chain of aligned electron spin. They will start oscillating. They are paired up with exchange interaction. It's also oscillating like a spring. That is give you a magnon wave. We also call it a spin wave. The interesting thing with the magnetic insulator is that it can propagate electromagnetic waves, can propagate phonon waves, and it can also propagate magnon wave or spin wave. Therefore, a magnetic insulator is very suitable for the study of magnetic metamaterials. And fortunately, the most interesting material I am going after for my study in terms of spin filter, the ferrite and the garnets, they were already heavily used in the photonic crystal construction. So our knowledge in these kind of magnetic insulators will also lead to the development in metamaterials. Now let's take a look at the history of the spin filter. The phenomenon of spin filter was discovered about 40 years ago. It was demonstrated that by European sulfide-coated tungsten tip, the emission current is almost 90% polarized. And there are even sophisticated schemes as to how to realize the spin polarized SEM. It did not work out because of very low Curie temperature of these European sulfides. So it's not suitable for low temperature operation. But if we are interested in other operations like spin polarized STM, scanning, tunneling, microscopy, it's no longer a problem. And the best candidate for spin filter and the most documented one are the elements based on rare earth and chalcogenide. Chalcogenide means the column below oxygen, like European oxygen, sulfide, selenium, tellurium. So these kind of materials are very well documented in the literature. The spin polarization is well above 98% using this material. The ferrite and the garnet material are the best candidate for the system to start working at room temperature. These are still low temperature operations. And there is an interesting class of material, the magnetite, like the lanthanum doped basement magnetite. This material simultaneously shows ferroelectricity and ferromagnetism. So such a system shows clear multifunctionality and can be used to construct, for example, a memory device based on magnetic random access memory and a ferroelectric random access memory. It's like combining two memory technology in the same system. We won't go into these details. Let's take a look at how we can use the spin filter phenomena for the construction of magnetic tunnel junction. The net result is that we can construct a magnetic tunnel junction without any magnetic electrode. Everything happens inside the tunnel barrier. So imagine we have such a system. We have non-magnetic electrodes and a hybrid tunnel barrier with two spin filters. If the two spin filters are aligned parallel to each other, the up electron will see a very low tunnel barrier and can cross the device very easily. Therefore, the system is in a low resistance state. Now, if the two spin filter barriers are antiparallel to each other, both the up and the down electrons have to cross at least one tau barrier to get through. The system is in a high resistance state. What we should see in the performance is that if we start with a very high negative field, the two spin filters will be saturated in the same direction, and we are in a low resistance parallel state. And at one point of the magnetic field, one of the layers will switch, and the system goes into a high resistance antiparallel state. If we keep increasing the magnetic field, the next layer will also switch. The system will return to the parallel and the low resistance state. This is the kind of the magnetoresistance curve we are going to see in our experiment. One very interesting feature of these spin filter tunnel junctions is that we can actually control the spin polarization of the transmission current. For example, I try to draw the spin up and spin down channels completely separately. If the two spin filters are aligned parallel to each other, the spin up electron will see two very low tunnel barriers and can cross the system very easily. And the spin down electron will be filtered out. They cannot cross the system. Now, if we look at the transmission current, it will be totally dominated by spin up electrons, and the spin polarization will be almost 100%. In the second situation, when the two spin filter layers are aligned opposite to each other, the spin up electron will see a low barrier and a high barrier. The same thing happens for the spin down electron. It sees the high and the low barrier. Their transmission are totally balanced. Therefore, we do not have any spin polarization in the transmission current. From this very simple cartoon, you can already see we can turn the spin polarization on and off by simply manipulating the tunnel barrier, the orientation of the spin filters. In addition, we can also simulate it. It shows that in addition to turn the spin polarization on and off, we can also turn it to any value in the middle. It's linearly tunable. So this is actually a real spin valve. We can turn the spin polarization on and off and set it to any point in the middle. It's like a valve. Now this cartoon illustrates how we construct this magnetic tunnel junction, the spin filter magnetic tunnel junction. It has two non-magnetic electrodes based on aluminum and a hybrid tunnel barrier with two spin filters based on European sulfide. There are two important things we have to address. Firstly, the magnetic anisotropy. We managed to take care of that by varying the deposition temperature. Let me show you the result. What we did is that we deposited the first layer at low temperature, the second layer at room temperature. That provides enough difference in the magnetic anisotropy, and this is the result. We can clearly see the two separate switching and a quite nicely defined antiparallel state. If we do not use the combination of deposition temperature, like we use low temperature, or room temperature, you can see we do not have this flat antiparallel configuration, and the TMR is significantly reduced. The next part we have to take care of is the magnetic decoupling. If we directly put the magnetic material on top of the other one, they will be strongly coupled to each other by exchange interaction. What we did is that we insert a very thin layer of non-magnetic insulator like aluminum oxide to magnetically decouple them. What happens is that if we don't have enough spacer layer, we reduce the thickness, the TMR value will significantly drop until it totally vanishes. Next, we take a look at the voltage dependence of these TMR devices. I start by showing you a standard magnetic tunnel junction, what it looks like. This is based on a system using MGO tunnel barrier. You can clearly see the magnetoresistance as a function of voltage is just decreased monotonically. There's no any feature. The reason is that when you use higher and higher voltage, the electrons have higher and higher energy. They are going to excite phonons and magnons in the tunnel barrier and the electrodes. Therefore, the TMR will be reduced significantly. Let's take a look at what happens with the spin filter magnetic tunnel junction. Please ignore the center part. This is pure noise because the device has a very high resistance. Two things you can notice right away. Firstly, the TMR behavior is non-monotonic. It goes up first before it starts decreasing. Secondly, it is asymmetric. On one side, the TMR is significantly higher than on the other side. So these two features are associated with the spin filter. And these three curves corresponding to different combinations of the film thickness, the two thickness. We have a thicker bottom layer, thinner top layer, or a thinner bottom layer, thicker top layer, all more or less the same. We can try to calculate what we are expecting in such a system. Let me first point out here that we did not use any fitting parameter. Everything was generated from the known values of the same system with the known values of the thickness. Now you can pay attention to the blue curve, the red curve, and the black curve. Let's compare. You can see the blue curve, the red curve, and the black curve. So we more or less capture the main features of the experimental result. Now we can take a look at why we see this non-monotonic behavior. This is because of the establishment of Fuller-Nordheim tunneling. The Fuller-Nordheim tunneling means if we have the two electrodes and the tunnel barrier, if we apply very high bias voltage, the tunnel barrier profile will be significantly tilted. When the voltage is higher than the tunnel barrier on the other side, the electron can cross the device by field emission, and its transmission probability will be significantly enhanced. In our situation, we have a spin filter. The spin up and spin down channels will establish Fuller-Nordheim tunneling at different voltages. And as a result, we see this significant difference in the magnetoresistance. The asymmetric behavior is clearly associated with the asymmetry of the tunnel barriers, and it can be explained by asymmetric establishment of Fuller-Nordheim tunneling. Okay. Basically, the talk you are seeing today was actually my review talk, like given yesterday. So I didn't have much time to modify many of the contents. So let's take a look at the future plan, which is a core part of an interview. So the first thing we can do in here at IQC is the construction of a superconducting quantum computers. There are many interesting proposals as to how to realize a quantum computer in a solid-state system. We can achieve error tolerance on the surface of these special systems. Let me try to explain just a very simple way. In a P-wave superconductor, we can take advantage of the voltage states and use them to create the so-called Majorana fermion. If you are not familiar with that, a Majorana fermion can be considered as a Hopper fermion, and it has a special properties. Its wave function is delocalized, so it's like entangled with each other, and so that they have non-locality, and their wave function is also protected because of the existence of certain surface states. You can perform breeding operations of two Majorana fermions to achieve any quantum computing. So this kind of Majorana fermion can also be constructed from a topological insulator. Topological insulator is a very interesting new state of matter, recently discovered only a few years ago. You can think of a topological insulator as a superconductor of spins. A spin current can flow on the surface of a topological insulator without any dissipation. We can try to create these Majorana fermions by using a proximity-driven topological insulator surface. We can also simulate a similar result by using a heavy metal surface with a strong Rashba splitting. Rashba, I think I shouldn't get into the technical details, but I want to point out here that all of these proposals involve the application of a magnetic insulator. The purpose of a magnetic insulator is to induce effective magnetic field on these surface states. And the application of this magnetic field will break the time reversal symmetry and open up a gap in the middle of Dirac cone. This is a core problem one have to address for all of these proposals. Next application of the spin filter is very important. We can use it for a single spin detection. It was proposed from IBM. Let's take a look at how this system works. Suppose you have a single electron wave function, and you want to find out if it's pointing up or pointing down. What you can do is you can apply a gate voltage and press the single electron wave function against a spin filter. Now, if you find the electron on the other side of the spin filter, you know it is pointing upward. Otherwise, they cannot come across. So if they are pointing downward, it will remain on the left side. So it's very easy to find out the spin information now. You just find out where the electron is located. This is commonly known as the swap gate operation in quantum computing, because what we are doing is actually turn a much harder to measure quantum, like a electron spin, into a much easier to measure quantum, like the position of the electron. We can do that much more with much better sensitivity. And another very important application of spintronics is to construct spin-based logic and memory units, like MRAM I have mentioned to you earlier. magnetic random access memory. With the novel technology, there are many different schemes how to realize such an MRAM. You can use a toggle switching or use a heat-assisted switching. The most advanced technology is based on spin transfer torque. I just want to mention to you the so-called storage trilemma. There is three fundamental problems, and they are totally tied with each other. So if we have a system is so stable, you will have a hard time to write it. And if you have you can address this stability and writability problem, you will run into a problem with the signal to noise ratio, which will typically require large volume to reduce the signal. So we normally refer this as the magnetic storage trilemma. When you solve one problem, you run into another. You create more problems. It's always like that. So the main problem is that in the magnetic recording, you have two stable states. We call it 0 and 1 states. They were separated by energy barrier. If the temperature of the system is so high, the states of the system will reverse. Then you lose your data. What we can do is we can increase the energy barrier to prevent that thing from happening. But then you run into the writing problem. If the barrier is so high, you will have no chance to write the information you want. And of course, these are also related with the volume of the device. If you have a big volume, it is stable, and it has a good signal to noise ratio, then you have a trouble to write it. Something like that. The next thing we can do with all these magnetic tunnel junctions is to build a totally new logic device. It is a very recent proposal from data. So in such a device, every magnetic tunnel junction can be configured into a sending or receiving mode. And the spin communication are realized by going through these channels using spin current. So it is becoming more and more plausible to build a total computer out of spintronics. You can perform all these logic operations. In addition, every magnetic tunnel junction is also its own memory. So we have a logic operation with their own built-in memory devices. So this is the direction we are going to come down in the near future. And because without knowledge in spintronics, it is good to take a look at many other different spin-based systems. Magnon laser is one of such a system. So this proposal is unique to magnetic insulators. The population inversion can be achieved by electron spin pumping. So what we do is we pump a huge amount of spin down electrons into the magnetic insulators. These electrons can go down to return to the valence band by emitting a magnon plus a phonon. Remember, the magnon is basically oscillation of a spin system, and the phonon is the oscillation of the lattice system. So what happens is that the emission of these magnons can be tuned into a stimulated emission. Once that happens, the magnon population will grow exponentially, and the magnon lasing will happen. Keep in mind, what is lasing now is a magnon. It's not a photon. It's different. The typical energy of a magnon system is on the order of millielectron volt, corresponds to terahertz. This is the beauty of the project. The terahertz radiation of magnon can combine with each other to emit a photon, which is also on the order of terahertz. If you are familiar with terahertz research, this kind of radiation can be used for security screening and for many different spectroscopy applications. So this is a very important field. Interestingly, the proposed model system, is actually based on European oxide, which we are already working on. We can deposit a very high quality European oxide in the MBE system. MBE stands for molecular beam epitaxy system. And we construct them MGO and European oxide-based magnetic tunnel junctions. We can take it one step further to look at their optical properties. Okay, The final few slides I prepared is to explain what our lab is going to be. The lab today is going to be focused on anisotropic magnetoresistance. We call it AMR. You've heard about GMR and TMR. AMR is actually an older technology. I'm not sure you guys even seen a floppy drive. The read head in the floppy drive based on AMR technology, very outdated. The good part with that is very simple to construct. What I'm getting is just a thin film permaloid. I will explain what that is. Let me start from explaining to you what the magnetization process is. We call it a hysteresis loop. Suppose we have a very high magnetic field. All the spins inside the magnetic material will be aligned parallel to each other. This is a saturation mode, and the magnetization of that in that configuration is a saturation moment. Now we start to changing the magnetic field, and at one point, the magnetization will become zero. So this is before that happens. What happens in the system is that the magnetic material will break up into domains. I mentioned to you earlier what a domain is. In the real system, it's actually more complicated. This is a very typical domain configuration. What you are seeing is that this magnetization here will create a lot of positive poles here, but they are totally balanced because this magnetic material will create a lot of negative poles here. So as a whole structure, the system does not have any net magnetic pole. So its magnetic static energy is zero. That's why the system will break up into complicated domain structures. When at a certain point, the system will go to zero magnetization. This position is known as a coercive field, this field. And you can consider it as a switching field. That's when the magnetization changes sign. Okay, now let's send in the current to such a device. This, in a real system, the domain structure will look more or less like that. You have a huge amount of domains along your structure. The basics for AMR is that if you send the current perpendicular to the domain configuration, you get the low resistance state. If you send the current parallel to these configurations, you get a high resistance state. So let me try to explain how the resistance will work. Suppose we start with a high field and saturated configuration. All the domains are aligned in the same direction, and now the system apparently is in a high resistance state. At the switching field, the coercive field, when the magnetization goes to zero, the system will break it up into domains like this, and the current will have to flow perpendicular to all of these domains, and the system goes into a low resistance state. And if we apply high enough magnetic field, all the domains will be saturated again. The system will return to a high resistance state. The real mechanism behind anisotropy AMR is because of the scattering of the localized D electrons and the mobile SP electrons. We should not get into the details behind that, but you can look it up, why the AMR happens and why when the current is perpendicular or parallel to the magnetization, the resistance are different because they have different scatterings. But there's nothing to prevent us from forming a domain structure, for example, like this, right? Now the current is actually flowing parallel, mostly parallel to the domain. And if the system goes into such a configuration, the resistance will actually increase at the switching field. Let me explain to you why there will be two such configurations. The first configuration and the second configuration are completely equivalent in terms of energy. The reason the system will prefer one from the other is because of the so-called magnetic anisotropy energy. Simply because for any material of whatever structure, they have a certain crystal structure, and because of the structure, there are certain directions for will be the preferred direction for the magnetization. For example, I put in a very simple cubic. The orientation of 0, 0, 1 will be totally different from a direction of, let's say, 1, 1, 1. And the system will have a preference for from one from the other. If the magnetic anisotropy orientation is in this direction, at 0 magnetic field, they will go to such a configuration because that will minimize the system energy. And if you send in a current, this configuration will give you a positive AMR signal. Suppose the anisotropy direction is actually in the vertical direction. The system will go to the ground state, will look more like this. And in the 0 magnetization configuration, you go to the low resistance. Therefore, in the same system, you can either get a positive or a negative AMR signal from the same system just by changing either the field orientation or the current orientation. And this is the reason why the system is called anisotropic magnetoresistance, because the system is totally anisotropic. It's angle dependent. Okay, our experiment will be a very simple structure. We have a thin foil. Actually, take a foil which is roughly 5 microns in thickness, and I cut into a rectangular shape with a length about 1 centimeter and a width roughly 1 millimeter. This material is commonly called a permalloy. It's a permalloy, a word out of that. It has 80% nickel and 20% iron. The unique thing of this alloy is because it has almost no magnetostriction. Magnetostriction is that when the system's magnetization changes, it will produce a strain on the system. Imagine you have a mass production product like a whole wafer. A very small magnetostriction will create a lot of stress on the system, and you are going to see a lot of cracks. The typical magnetostriction is actually not very large. They are like parts per million. But that is large enough for a large wafer. You get a lot of defects out of there. Therefore, people developed this permalloy. It essentially has no magnetostriction. Another nice thing about it, it has a pretty high AMR signal, roughly 5% at room temperature. So if we send a current in along the wire and monitor its change as a function of field, what we really see is something around 2% you are going to see in the lab. And by now, I'm pretty sure all of you have already heard about the 4-terminal measurement. So I basically used epoxy to glue my wires onto the two ends. And I'm going to send the current in this way and monitor the voltage on that way. In this configuration, we do not measure the resistance of these wires. And in the lab, what you are going to see, we can apply the magnetic field along the current direction, and we can also apply the magnetic field perpendicular to that. You will see the sign change of the magnetoresistance. Okay, so that's all the slides I have for today, and almost good time to stop. Yes, I have 15 minutes. Yes, go ahead.
So with your spin filter, it seems like, maybe I'm not understanding it correctly, but it doesn't seem like it's 99% efficient. Are you talking relative efficiency? Like it discriminates with 99% efficiency, or is it absolute?
It's like a relative, which means basically you have 1% of down electron, but 99% up.
So what is its actual absolute efficiency though?
Theoretically, it will be nearly 100%. It will be much higher. The reason is that you remember this is based on quantum tunneling. This is exponential. A very small difference in the tunnel barrier height will end up as almost total filter of the other spin. So their efficiency are actually extremely low. Theoretically, experimentally they see something like 98%, which is basically means the 1%, 99%. You see 1%, basically 99 minus 1 give you 98%. So that 1% will balance another percent.
With the Magnum laser that you talked about just briefly.
Sure. Yeah.
I'm not sure. Isn't the photon radiation going to be very incoherent?
It's Actually, it won't be. The lasing will be in the magnon. The magnon are phase coherent.
Yeah, but you're talking about the photons being created from analysis.
Yeah, photons from magnon will not be phase coherent. So it's a nice light source, but it's not a coherent source.
Yeah.
What is lasing is magnon. Photon is like a byproduct, although this is what we want.
No, I understand. It's just you're presenting this as being a source
it's
of
a magnon laser. Yeah, indeed, it's not a photon laser. It will be a very nice terahertz radiation source, but it won't be a laser source. Yes.
On the next slide, or maybe 2 slides now, your all-spin device.
Oh, okay.
Yes. Yeah, can you just go over that again? I didn't quite understand that.
Okay, so what happens is you see this complicated channeling combination. So each of them can send out a spin polarized current. This is based on spin transfer torque. And by combining them, for example, you can combine a spin up current, spin current, and a down spin current. You can perform this AND and OR operation by combining these channels. And if you reverse the polarity, you can perform this NOT operation. So basically, by combining all these features, you can perform all these 4 fundamental logic operations, which means you can do everything else. So they are capable of performing all logic operations, and each of them is also a memory of itself because they are MTJs, so they are basically MRAM on their own. So you have a computer with logic, with the memory, everything together, and mediated by spin current, all the communication. You combine all these channels for different operations. Any more questions? No? Okay. Yeah, go ahead.
How resistant to, I don't know how to put this, but noise decoherence is a spin polarized current over, I don't know,
they have
macroscopic distances. Times.
They can travel microns easily, but one thing built in here is that every signal only reaches this far. Beyond that, it will be, there's a blocker. So all you need is to propagate your spin information from here to here. You don't need to go beyond that. And this system will continue. It's like sort of like the transistor performance.
Mm-hmm. But it's not like at room temperature you could do long-term.
It's not yet. In the metallic system, you can get coherence up to microns. So these things will be very close together. So even at room temperature, they are microns, but micron is kind of crowded already. The device will be like 100 nanometer or less.